Now we'll think about Newton's law of gravity. And at first this might seem a little different from the way we've been talking about weight, the only gravitational force we've talked about so far. But at the end of this, we'll see that they're really two different versions of the same thing. So the basic idea is that anything with mass feels a gravitational force, and anything with mass will also exert a gravitational force on other masses. The gravitational force is always an attracting force. So here's two masses, mass 1, mass 2, and they each apply an attracting gravitational force to the other. The gravitational force from 2 on 1 pulls 1 toward 2, and the gravitational force from 1 on 2 pulls 2 toward 1. That's all we have to say about the direction of that particular force. What about the magnitude? We have a nice rule to tell us the magnitude of a gravitational force. There's this constant factor, capital G, you can look up. Don't confuse it with lowercase g, 9.8 meters per second per second. You can look up this number if you ever have to do any calculation. And then comes the product of the two interacting masses, and you divide all that by the square of the distance between the two masses. The distance between here and here. Often it's called r because sometimes we'll be dealing with circular situations, but this isn't necessarily a radius. This is always the distance between the two masses. And in some circumstances, it will amount to the same thing as a radius. Now, the way I write it is that here, thing 1 is the source of the force, and that force acts on 2. So the source of the gravitational force, I put its mass in the first slot, and the thing that's acted upon by the gravitational force, the thing that feels the gravitational force, I put that in the second slot. So let's look at the other force here. Instead of the gravitational force from 1 pulling on 2, let's look at the gravitational force from 2 pulling on 1. So G, and then in the next slot goes the mass of the source. This is a force from 2 pulling on 1. And then in the last slot goes the mass of the thing that's feeling the force. Mass 1 is pulled by mass 2. But look, here in the numerator we've got m1 times m2. Here in this numerator we've got m2 times m1. Same thing. Multiplicate. The order in which you do multiplication doesn't matter. So all the same factors here and in this numerator, same factors in the denominators, the magnitudes are the same. Or to put it another way, the vector force, the gravitational force from 1 on 2, is equal in magnitude and opposite in direction to the gravitational force from 2 on 1. They're a third law pair. Those two forces, these two forces, the force from 2 on 1 and then the force from 1 on 2, are a Newton's third law pair. And remember the characteristics of a Newton's third law pair. They're both the same type of force. They're both gravitational forces in this case. And the two forces in a third law pair point in opposite directions just like these do. And they have the same magnitude. Right? The rule for the magnitude of one force is just the same as the rule for the magnitude of the other force. And then in a third law pair, you've got a force from one thing acting on the second thing, and the other force in that third law pair is the second thing acting back on the first thing. all the characteristics of a third law pair in this gravitational force. And one consequence of these gravitational forces being a third law pair is that, in a sense, it doesn't matter whether the masses are the same or different. Even if the masses are very, very different, the two forces will be equally strong because they are the two elements of a third law pair. Just spell that out a little more explicitly. Let's say you've got one thing here with a mass of m and another thing here with a mass of 1,000 m. And so there's a gravitational force from, call these things A and B, just to be a little, make reference easier. So there's a force from B pulling on A, pulling A towards B, and then there's a gravitational force from A pulling on B. A is pulling B towards A. Let's just explicitly spell out the rule for magnitude of force in the case of the force from A on B. Gravitational force from A on B is just the gravitational constant, and then the next term is always the mass of the source of the force. And this is a force from A. A's got a mass of just plain m. And then the next term is the mass of the thing that is feeling the force, the thing that is acted upon by the force. And in this case, B is acted upon by the force. B is pulled by that force. And the mass of B is 1,000 m, or I'll just simplify it as 10 to the third m. And then we'll say that the distance between those two masses is just d meters. So in the denominator goes distance squared. Now, gravitational force from B on A. B is the more massive thing. But just because it's more massive, that doesn't result in a stronger force coming from B. It'll be just the same force because these two forces are a third law pair, so they have to be equal. In this case, first term in the equation for the magnitude of this force is the gravitational constant g, and then next comes the mass of the source. B is the source. This force comes from B and acts on A. And the mass of B was 1,000 m, 10 to the third m. And then the last term will be the mass of the thing that feels the force. In this case, the force acts on A. A feels the force. The mass of A was just 1 m. And that's divided by the distance between A and B. Divided by square of the distance. And of course, here you've got g times mass times 10 to the third. Here you've got g times mass times 10 to the third. All the same factors. So the same number in both numerators, and of course the same number in both denominators. These two forces are equally strong, even though they have very, very different masses. It's sometimes it's hard to get over that fact. you focus so much on the fact that they have different masses, it becomes easy to forget things that you actually know, like Newton's third law. It becomes easy to forget the fact that the force from A on B, and then the force from A on B and the force from B on A are a third law pair. And once you say that, you know they must have forces of equal strength, even though they don't have similar masses at all. You could think of it this way. B has a much bigger mass, so that allows it to create stronger forces for any force that has B as the source. But when B has more mass, that also means it's going to be 1,000 times more sensitive to gravitational forces that come from other places like A. So this 1,000 makes forces 1,000 times stronger when those forces have B as the source, but this 1,000 makes forces 1,000 times stronger anytime you have a gravitational force on B, as well as gravitational forces from B. It's 1,000 times more sensitive to gravitational forces that come from somewhere else, like A. So the force from A on B will be just as strong as the force from the big mass on the little mass, the force from B on A. Let's take one other aspect of that equation for magnitude of gravitational force. Magnitude of the gravitational force from thing 1 on thing 2 is just 3 factors here. Gravitational constant, the mass of thing 1 and the mass of thing 2, divided by the square of the distance between thing 1 and thing 2. Let's imagine that we're always watching the same 2 things. We're always watching the same interaction between the same 2 things. So M1 and M2 don't change. G doesn't change. The only thing that might change is the distance between the 2 things. Say one extreme example of that might be, let's say, a comet revolving around a star, a comet in orbit around a star. Comets have very, very elliptical orbits, not very circular at all. So there's the star that the comet orbits around, and typically a comet's orbit might look like that. So the distance between, in this case, if we're looking at gravitational interaction between the comet and the star, the distance between M1 and M2, the star's mass and the comet's mass, will vary quite a lot. Right? These 2 numbers don't change. This might change a lot. Well, let's look at one specific example of that. If the gravitational force is always between the same 2 objects, everything in the numerator is constant, and the only variable factor on the right-hand side of that equation is square of the distance between the 2 things, now you've got an equation that fits a pattern that we recognize, the pattern for inverse proportionality. Anytime 2 variables, y and x for example, are inversely proportional, they can be related in an equation like this, where c is just constant stuff. C is just a constant factor, or like in this case, the product of some constant factors. What happens in inverse proportionality? Well, we've already seen that when talking about the relationship between acceleration and mass in Newton's second law. When in inverse proportionality, when one variable changes by some factor, so inverse proportionality, and let's say x changes by some factor. The second value of x is just n times the first value of x. Because it's inverse proportionality, we immediately know how the other how the other variable y changes. This implies that y must change by the inverse of the factor. y2 is 1 over n times y1. If n is greater than 1, then that means x got bigger, and then y got smaller. And that's always the way things work in inverse proportionality. When one variable gets bigger, the variable that it's inversely proportional to gets smaller. So let's compare, say, the gravitational force on the Earth to the gravitational force on Venus. That's a good comparison to use because the mass of Venus is pretty close to the same as the mass of the Earth, about 83% of the Earth's mass, close enough that we can say all the factors in the numerator are the same, whether we're talking about the gravitational force from Earth, gravitational force from Sun on Venus, or gravitational force from Sun on Earth. In either case, it's a gravitational force from the Sun, so the mass of the source goes in this slot, and then it's acting on a planet, so MP. A planet, either Earth or Venus, feels that gravitational force, and since they have roughly the same mass, we'll just use an approximate model in which they both have the same mass, and we'll call that mass MP. The only thing that differs, the only thing that would make the gravitational force felt by Venus different from the gravitational force felt by Earth is that they have different distances from the Sun. And in particular, the distance from the Sun to Venus, or average distance over one complete year, one complete Venusian year, is about about 72% of the average distance between Sun and Earth. So we have that. And you can, as it turns out, the magnitude of the force from the Sun on the Earth is roughly something like this. Let me be sure I get my numbers right. About 3.5 times 10 to the 22 newtons. And since the strength of the force and square of the distance are inversely proportional, not the distance, square of the distance, because when you compare the way the gravitational force equation looks when you're keeping masses the same to the general pattern for inverse proportionality, what the general pattern here tells you is that after you've lumped all the constants together, the only thing that's left is the variable, and it's in the denominator. And here, in the gravity equation, we've lumped all the constants together, capital G, mass of the sun, mass of the earth, and everything that's left over is the variable, and it's in the denominator. Well, what's in the denominator is d squared. That's the variable that is proportional to force, just as x, what's in the denominator, is proportional to y. Whatever is in the denominator is inversely proportional to the other variable. What's in the denominator here? Not d, but d squared, and that's proportional to force. So d squared is inversely proportional to force. So if we know how d squared changes, we can see how the force differs between Earth and Venus. Here's how d differs, but we need to know how d squared differs between the Earth distance and the Venus distance. We need to know d squared because it's d squared that is inversely proportional to the force. So we can get that easily from this. You square the whole equation. And then we have sun to Venus distance squared equals 0.72 squared times sun to Earth distance squared. So this variable called distance from the sun squared, one distance from the sun squared times this factor, 0.72 squared, gives us the other distance from the sun squared. So this is the factor, 0.72 squared is the factor by which distance from the sun squared changes. And distance from the sun squared is what's inversely proportional to force. So square 0.72 and it comes out to about 0.52. So 0.52 is the factor by which d squared changes. Anything that it's inversely proportional to will change by the inverse of that. So magnitude of the force, the gravitational force felt by Venus, is 1 over the factor, the inverse of the factor, times the gravitational force felt by Earth. And we said that this was about 3.5 times 10 to the 22. So take that 3.5 divided by 5.2, and the magnitude of the gravitational force that Venus feels from the sun is about 6.7 times 10 to the 22 newtons. Not quite twice as strong. And we just used inverse proportionality to figure that out. We didn't need to bother with the actual mass of the sun or the actual mass of the Earth or mass of the mass of Venus. We didn't need to even know the specific distances from Earth to Venus and Earth to Sun. All we had to know was that was the relative size of those two. Right? Venus's distance was about 72% of the Earth's distances. That's all we needed to know. So there's a lot more that we can do with all this. One last thing. How is this related to weight that we've been talking about? Now just think of the gravitational force from an object, the gravitational force felt by an object sitting on the surface of the Earth. that's a kind of gravitational force that we've been calling weight. But it's a gravitational force, so it ought to obey Newton's law of gravitation. So it ought to be the case that the magnitude of the gravitational force from the Earth on some object sitting at the surface of the Earth ought to be simply the gravitational constant times mass of the Earth, the mass of the source of that force, times mass of the object, mass of the thing that's feeling the force, times the distance between the object and the Earth. Well, what does that mean? The object is sitting right on the Earth. Isn't that distance zero? Well, not quite. Because one little wrinkle in Newton's law of gravitation is that those distances are all measured from the center of each object, from the center of one object to the center of the other object. So in this case, the square distance is actually the distance from the center of the Earth to where that object is on the surface of the Earth. In other words, that distance in this case is going to be the radius of the Earth. And it's always distance squared. So if we combine some factors here, g, mass of the Earth, radius of the Earth squared, combine them and separate them from mass of the object, now we actually have our rule for weight. This is simply equal to g times the mass of that object, because that is g. You multiply all those factors together and you will come up with 9.8 meters per second per second. That's why g has that particular value of 9.8. And if we were, say, on a planet that had roughly the same size as the Earth, but less mass, then g would be smaller. And continue with more of this in class.